Right.
Okay, so this is lecture 10, where we're going to talk about entry regions. Whoops. Let me start over.
I'm going to clip that off the... Oh, that's... Not looking at the PDF. Okay. Take 2.
Okay, have I got it? Yeah. And... All right. Okay, so this is lecture 10, where we're going to look at entry regions versus fully developed flow. Whoops. Okay, we're going to talk about concentration boundary layers, concentration profiles. We're going to use a reactive surface that produces something that diffuses into the center. And we're going to look at the entry region versus the fully developed region. We'll talk about what that is and apply that to different examples. Oops. Okay, so that's the same thing. All right, so the first thing to remember about what we're going to be talking about is that we're looking inside of a pipe now. It's not flow over a flat plate. What we're doing is we're looking at flow coming into a pipe. So this is just one wall of the pipe, and the other wall is up here somewhere. And this is the center line of the flow. And we have... This is the beginning of the pipe here. So the flow is coming in. It's got a concentration of CB0 at the center line at R equals 0. And this is a reactive surface, and she explained it as being like a biomaterial that might be generating thrombin. And can I take that off? Yeah. So, what she's showing here is that the concentration at the wall is high, and I want you to look at this by turning your head counterclockwise, so that this is the axis. This is the axis for the radius, and this is the axis for the concentration. And so this is a high concentration near the wall, and it's decreasing to, in this case, almost 0 at the center line. Okay, as we move further down the wall, this boundary layer here, you can see the width of the boundary layer right there, and it's del. It increases. It keeps getting bigger and bigger. And if you want to, whoops, here, I'm not good with this.
My iPad software upgraded last night, and now it's throwing us off.
So I'm going to draw, this is the tube, and so you can see what happens in the Levesque, in the entry region. Do you want to use
a different color?
Oh yeah, let me use red. So as we come in here, and right now I'm talking about the velocity. I'm going to draw the velocity. So if it's all coming in here like this, so everything's at the same velocity, it hits this wall here and it gets slowed down. So if you draw the velocity profile, you're going to see that it's something like this, where most of everything doesn't even know that we've hit a wall, and just here up next to the wall, the velocity has decreased. As we go further downstream,
and let me zoom you in on this.
Oh yes, that would be helpful.
There we go. So as we go further downstream.
As we go further downstream, this is the boundary layer thickness there. That del, which is a function of the distance. Let's call it z in this case. X. We'll use x. So del is a function of x. So it increases as you go further downstream.
I'm gonna make the boundary layer here in blue, so it's really tiny here, and then it just gets bigger, and then it gets bigger.
Right.
And it goes on the other side.
Yeah.
So it's symmetrical that way.
Right. So if I go back to the red, so that, yeah, it actually becomes, as you go, whoops, as you go further downstream, the boundary layer, yeah, whoops. The boundary layer is going to keep getting bigger and bigger until it meets at the middle, and then you've got a nice parabola right here. And so if let me take another color, yellow. So if I draw the width of the boundary layer, it looks something like this until it reaches the center line, and we have fully developed flow. Okay, which I haven't finished. Whoops. I'm not good at this. Which I haven't finished here. So we will reach a point where we have a parabola here, which you're going to calculate when we get into fluid mechanics. And the boundary layer, whoops, it should be yellow. And the boundary layer is going to meet at the middle, and now you've got fully developed flow. Okay, so that is the boundary layer for the fluid flow. I'm not an artist, but anyway. So the boundary layer for the mass transfer is going to do almost exactly the same thing. So I won't draw it again, but it looks almost exactly the same. It just might take a shorter period of time or a longer period of time to reach fully developed for the concentration profile.
And so what I think I'm hearing you say here is, I'm going to get the pen out so I can point at things. So this picture that we've done down here is kind of the long-term big picture of this whole system. And then up here we've got we have a split into two regions. Right, one which is before there's fully developed flow, and one after.
Right.
So that's like this.
That's the fully developed area.
Fully developed, and then while it's ramping up, that's the, how do you pronounce that?
Levesque.
Levesque.
Or the entry region.
Entry region.
Yes.
Entry region's much easier, but
yes.
Levesque. Okay.
Okay, so that's all that's going on here. And I think that's, yeah. Oh, the one thing that she was saying here is that the K sub L, and in this case she's using K sub L, I think she means L for local. So the local mass transfer convective coefficient is a function of X in a pipe until we get to a fully developed region, and then it's constant.
This iPad software update is really annoying.
All right. Okay, so in this case, we're going to look at large diameter short tubes. And basically, the importance of this is that it takes several diameters downstream before you're fully developed, especially for laminar flow. So if you have a large diameter or a short tube relative to the diameter, then probably everything's going to be in the entry region.
That makes sense because it just doesn't go far enough to develop that stable, fully developed flow.
Right.
State.
Right. And just think of it in terms of diameters. How many diameter lengths, how many diameters downstream are you? Okay. And by the way, if it's turbulent flow, it doesn't take as many diameters downstream to become fully developed. Okay, and in this case, she was talking about if you have a very small diameter, but it's actually the same thing. It's just how many diameters downstream are you. And I'm just going to throw a number out. Let's say like 25 diameters before you become, before it becomes fully developed flow. And I'm just pulling a number out of the air that it changes for different Reynolds numbers and so forth. But just to give you an idea. Once it's fully developed, of course, the local convective mass transfer convective coefficient is constant. All right, and let's look at this one. Here, what you do is you go to that table that we had in the last lecture, and you can calculate the Sherwood number from the Reynolds number and the Schmidt number. Right, so you've got correlations in order to find the Sherwood number, and then the Sherwood number we saw was just the convective coefficient, the local one, let's see, times some characteristic length, which in this case we're going to call, oops, she's using small d, diameter, divided by the diffusivity. That was the Sherwood number, the local. So all she did is she took this and she solved for our convection coefficient. So that's all that is. All right, we already talked about this. Okay, so what we've done was for nice, straight, cylindrical pipes. But a lot of times you don't have a nice, straight, cylindrical pipe. You've got complex configurations.
Like blood vessels.
Yes, like the real world. And so she's showing you how you could find a local convection coefficient. And one of the things that she's talking about here is the shear rate, which is, shear rate is gamma dot. Gamma dot is the shear rate. And as you will learn when we get into the fluid mechanics portion, the shear rate is just the gradient of the velocity with respect to r, in this case. Okay, so right up against the wall, this value is kind of high, and when you have a reactive wall, that's the gradient that you're concerned about. So she was showing you a way that you could estimate what the local mass transfer convection coefficient would be. Okay, so you would have the shear rate. Here, let me blow it up. The shear rate, this is, in this case, big D is for diameter. Mm-hmm. This is the distance downstream. And it's all to the power of 1/3.
And we were talking just before we started filming about how shear rate may be something that might be a new concept to some of you. And so shear is just like plates sliding past each other. And
right.
So shear rate here, do you sort of have a way to conceptualize like physically what? I have my hands together, I'm like rubbing them together here.
So yeah, so this is the velocity in the x direction, and there's a gradient in the perpendicular direction. Okay, which makes it shear.
Yeah, it's harder to do this when we're drawing on slides, but
yeah, and we're going to talk a lot more about shear rate in fluid mechanics, so that's coming up.
So this is not something that, if you're going, oh no, what's shear rate? We haven't talked about that before. You are correct. We have not.
One interesting point that she made is that the local mass transfer convection coefficient varies with the shear rate at a power of 1/3. So it's only a modest effect of the shear, but as you will find out in the fluid mechanics portion, there's a big difference in the shear rate between arteries and veins, which is, it's much higher in arteries than it is in veins. And that's why you see the thrombi, oh dear, the thrombi occurring in arteries different, at a different rate than you do in veins.
I want to know why now, but I can hold those questions.
Yeah. There's also other issues in terms of high shear rate is one thing, low shear rate is another thing. But for now, just know that it's different, and so it impacts this mass transfer coefficient.
So we will see shear rate again, and all these curiosities about, like, why is it different will come up, but you don't have to know that right this moment.
Right. She gives some ranges of physiological values for the mass transfer coefficient, so that you can have an idea. You can have an idea of what the values, what ranges there might be. Let's see. Then she talked about hot spots, meaning that maybe you might have, oops.
Mm-hmm.
Yeah. I did it again.
Maybe you might have.
Maybe you might have. So this is a pipe. We've got a wall here, and we've got a wall up here. But she was talking about maybe you might have a thrombogenic hot patch right there, just on one side and not on the other side.
So this is the electrical engineering question. What is thrombogenetic?
Oh, excuse me. Something that is producing the thrombin and encouraging coagulation.
Okay, so thrombosis is like clotting of blood.
Yeah.
Okay, got it. Thank you.
I'm sorry, Han.
I was expending all of yesterday's lecture going, I think this means clotting.
Yes.
I think.
Please do call me out whenever I use a word that...
Well, no, I mean, this is, you're a biomedical engineer, so you probably know this, and I'm just going, new vocab. Medical stuff is new for me.
Okay, and here she's giving an example of the blue wall here is a biomaterial with blood flowing through it, and the red is, I mean, the entire tube is filled with blood, but the red is the boundary layer portion, so that you can see how the boundary layer is growing as we move downstream.
Okay, keep going.
Okay. Let's see. She also...
I'm gonna label it with colors as you keep talking.
Oh, okay.
Go for it.
Okay, she also talked about how thrombin can auto-accelerate its production. So the more thrombin you have, the faster it can produce.
Okay.
So that's, can I draw with my finger? Yeah, that's what that is.
Mm-hmm.
All right, and so here's the reaction rate. So if CW is the concentration at the wall, and Kp is our reaction rate constant. Okay, so the idea here is that the more thrombin you have, the faster it can produce. If you're transporting thrombin away from the wall, we're using this equation. It's convection, so this is the convection coefficient, and this is the difference in concentration between the wall and the center line. So that's the rate that it's being transported by convection. This is the rate that it's being generated through the accelerative reaction rate. And if it's being produced at the same rate that it is being convected away, then we can equate those two. And, whoops, I did it again. And here we can just solve this equation and rearrange it to find the concentration of the wall over the concentration at the center line. And now we're just going to graph this relation.
Dun, dun, dun.
Yes, so this is just a graph of this equation. That's all that this is. But it shows that as this ratio increases, then the thrombin concentration becomes huge. And so obviously you want to keep this relation somewhere down here, let's say from this area and lower, so that you don't have this huge increase in thrombin production.
So this is basically how to not get a blood clot?
Yes, how to decrease the chances that you'll get a blood clot. Okay. Oh, and before we go on, she talked about different materials, how you could add heparin to a particular material, and it would decrease KP and bring you from from the region up in here down to a region, a better region down here.
It might be time for us to get different PDF annotation software for these videos.
All right. Now here she's just giving you a table of different values for these. So you can look for a cylindrical tube. You can look for different values of the production versus L and find KL or the mean. Let's see. This is the entry region. This is the fully developed region. Okay, so that's all that is. And I'm going to pause it for now.
Okay.
And we can complete this later if you like. But that's the end of this particular portion.
All right.